So let's see. I'll have my usual office hours today. And I remind you that there won't be class on Wednesday. I'll be on travel. So we'll try to find some time for a makeup lecture. There's one other travel date I know that will conflict with the lecture, so we'll try to think about when we can find a time that would work for most people. All right. I remind you that we're not moving on the week of the 21st. That knows that we'll actually move. But I assume it'll be before Thanksgiving. Anyway, we'll be here for a little while. All right, very good. So let's see. So last time we introduced a very important concept that will be developing with increasing sophistication over the course of this academic year. We have introduced the concept of the master equation so far from a phenomenological point of view, introducing a kind of damping coefficient into the optical block equations in the same way that we introduce damping into the simple harmonic oscillator without deriving it from first principles. But I promise you we will derive it from first principles a little bit later in the spring, all right? But there are some important things we discovered, interestingly, just doing this phenomenologically. So we're looking at these quantum systems with dissipation. In particular, the problem we're focusing on at the moment is something like an atom which can spontaneously emit, and we notice a number of important features of the dynamics in that situation. Firstly, the dynamics of the quantum state is not described by something that we would say is unitary evolution. It's non-unitary. It's irreversible. And it's not described by the standard time-dependent Schrödinger equation. Okay? So all of those things really follow from the fact that what we're talking about is what is generically called an open quantum system. Right? Meaning the following. We have some quantum system we're interested in, for example, our atom. But that atom is not isolated in the world. It is sitting in some kind of environment. And that environment might be the electromagnetic vacuum. Even if we were to isolate the system from all material goods, it would be still embedded in the electromagnetic field that pervades the universe in the way of vacuum. And through that interaction, if we don't take the whole system, including both the atom and the vacuum, and we just look at a subsystem, the atom alone, then the system is open to the world. And it's through that coupling to the world that these weird features arise. Okay? And as I say, we're going to talk about this in much more detail. Over time, we need to think about the quantum mechanical vacuum before we get there. But it just is a little prelude of things to come. Okay? So what we discussed last time is a number of important facts that we discovered in looking at the optical block equations, which is phenomenological T1 and T2. It seems like an easy thing to do, and we got all kinds of goodies in the process. One well, we said, well, how far can we get, as is often done in kind of a more traditional quantum mechanics, from the 1950s, is to just say, well, if I have some decay, all I'm going to do is add an imaginary part to the unstable energy level that depends on the lifetime of that level. That lifetime is tau, then there's some rate, 1 over tau, and I can just add this imaginary part, which would account for a decay in the probability to be in that state, right? Which goes like e to the minus count t. And that would equivalently say that the Hamiltonian that describes a system has an imaginary part, or anti-Hermitian part, right? So this is a non-Hermitian Hamiltonian. And I can ask, well, I'm just going to look at a generalization of the Schrödinger equation that instead of having a Hermitian Hamiltonian has this non-Hermitian Hamiltonian in it. And what we showed is that gets us pretty far. In fact, that would describe a system of this sort where there was some auxiliary level to which this level decayed. Because one of the things that we note about such an evolution is that the norm of the vector, the ket, is not preserved, right? And that means the probability to be in the Hilbert space somewhere isn't preserved. And that is a physical situation that we might be interested in sometimes if we only look at a subsystem not a subsystem, a subspace, not a subsystem, that's a different word, means different thing. So I have 3 levels, but I'm only going to look at these 2 levels. Then if this level decayed to this level, and you only looked at what happens here, then the probability to be somewhere here would decay. It would go to 0, because ultimately it would go here, especially if I'm driving the system somehow between these 2 levels. Okay? So it's not a crazy thing to think about such a kind of Schrödinger-like equation with a non-Hermitian Hamiltonian. We use that for this kind of situation all the time. But if we have something where we had also possibility of this system decaying back to this system, and that we would say would be a refeeding term. Somehow the population in this state has to grow in some way. There's no way to account for that by adding an imaginary part to the Hamiltonian. In fact, there is no deterministic evolution by a differential equation of any pure state that would describe such an evolution. In fact, such an evolution would require us to now think about the density operator. And in fact, that's not surprising if we come back over here to this board and just think about the fact that we have an open quantum system. And if we have an open quantum system, then if we're not taking into account the information that goes into the environment, then we're losing information about the system. And as we have discussed, a pure state represents our complete knowledge of the quantum system. And if we no longer have complete knowledge of the quantum system, if we're losing not only energy, but information, well, then it's not surprising that the state of the system becomes mixed in some way. All right? And so that equation is generally written of this form, where we have the unitary part of the evolution due to the whatever Hamiltonian describes our system, and then the interaction with the environment leads to another term, the relaxation term in the master equation. Okay? And the specific form that we're looking at here is known as the Lindblad form, or Lindblad. And that is not the most general form, but it's the most general form we'll deal with in this course. And it's an excellent approximation in quantum optics, as we will see. And it has some new players in the game. The most important thing is we have this new thing we call the jump operator. And generally there can be more than one jump operator. There can be multiple jump operators. And the Lindblad form has this form where this is the relaxation part of the master equation. Okay? And moreover, we can lump together these terms with the Hamiltonian in terms of an effective Hamiltonian that looks like this. And it has the Hermitian part, which is the good old, our friend the Hamiltonian, and then this imaginary part, or anti-Hermitian part, which depends on the jump operators. And when we group things together that way, then what we see is the master equation has two pieces of it. One having to do with the non-Hermitian evolution that's really just a operator version of these. These two equations are exactly the same, just written here in terms of the density operator rather than the state vector. But then there's this additional term here which is new. And that term is the refeeding term. And there's no way to account for that, as we will see, by some differential equation, deterministic differential equation on the state that stays pure. So somehow this is related to something stochastic. It's our favorite word for random. There's something random going on. We're losing information, and that randomness is the notion of a quantum jump. And somehow this is related to the idea of the quantum jump. And it's that when that, because we don't know when that quantum jump is going to happen or if it's going to happen, that we don't have full information and why the system becomes mixed. Now we will derive all of that from first principles next semester, but we see the seeds of it already. Okay. Now, I want to just write this equation down, the master equation for the particular case of the two-level atom that spontaneously emits. So, driven two-level atom in the vacuum. So we have our problem here. We have our two-level atom. We are driving it with some Rabi frequency, be tuned some amount, and can spontaneously emit with some rate gamma. All right? So, in this problem, our Hamiltonian in the rotating wave approximation, as we have discussed, for many lectures now is that, where I take the laser phase to be 0, and the jump operator in this case corresponds to spontaneous emission, which causes the system to make a quantum jump from the excited state to the ground state. Okay. So our jump operator here is sigma minus, and it has units of the square root of time, square root of rate, and it has that coefficient in it. So that's our jump operator. There's only one of them in this case. It's that guy. Okay. So this is equal to square root of gamma So the master equation in this case has this form. So that is the master equation for a two-level atom being driven by the laser and in the presence of spontaneous emission. This is an operator equation, and we can look at its matrix elements and from that get the optical clock equations. We kind of went in reverse, right? We started with this and we added in damping, and then we kind of showed that this is the form. But this is the general equation, right? This, if I plug in here, this is, of course, plugging in for the sigma plus and sigma minus. Sigma plus times sigma minus is the projector onto the excited state. Okay. So I can also write this equation as this is the population in the excited state, so that's this term, and here H effective is H minus I H bar gamma over 2. This is sigma plus sigma minus. This little prime here is just a shorthand for the fact that when I do the commutator, I gotta put the dagger over here because it's not emission. Okay. So this is of this form. All right. Now, let's just write down the matrix elements of this equation. And write them up above here. So for this equation, what I have is, when we did that equation, we get the following. I gotta get the signs right. I've been struggling with these there's so many damn minus signs in this problem. And it's just like it comes almost a randomized, whether it's plus or minus. By the time I've done it 5 times, I can't remember anymore. But let's see. So that is the master equation written in terms of the matrix elements. And of course, this is equal to that because for my two-level atom, the total population, if I don't have an auxiliary level into which anything can decay, the total population at any time must sum to 1. That's the trace of the density operator is 1, or said another way, the total population to be in the ground state and excited state adds to 1, assuming there's no auxiliary level. So that means I don't need to write down a separate equation for rho GG, it's just the minus of this equation, because they have the total derivative of this is 0. Okay? And similarly, this equation gives me the other equation for the coherence, because that's just the complex conjugate, right? Because it's a Hermitian matrix that transposes the conjugate. Right? All right. Very good. So this equation showed, if I were to ask what happens to, in this equation, just to remind you, what if I looked at the population to be in the excited state as a function of time? Let's suppose that my initial condition was that I put the atom in the ground state and then I suddenly turn on the laser. What happens as a function of time? If I were to ask what happens to the population as a function of time? Decaying oscillation. So in the absence of decay, we get Rabi oscillations, right? And in the presence of decay, we get what we call damped Rabi oscillations. So for example, if I was, near resonance, I would see something that doesn't go quite to 1 anymore, but something that would ring and go to some steady state. Okay. Now, what that steady state is depends on the detailed balance of the decay rate versus absorption. So what we're going to do today is just do a little bit of standard laser physics to see how our steady state evolves, and to think about this also in relationship to what we studied in the first week of the semester, or maybe the second, thinking about a charge on a spring and how the system, if I have a driven oscillator of a bound electron to a nucleus, how we get absorption emission and get a steady state dipole. Okay. So let's think about this in the following way. So what I'm interested now is, so let's say I want to ask the question, what is the induced electric dipole moment of the atom? After transients die off, right? So in the same way that we thought about a charge on a spring that was driven, we saw that it came to some steady state and we had some induced dipole moment. What's the induced dipole moment of the atom? How would I calculate that? Any thoughts?
Population version?
Well, I can calculate something about the population version for sure, and that's in some sense related to this. But if I ask the question, what is the Well, I asked, maybe let's just strip off all the complication. If I asked you, what is the dipole moment of the atom, how would you calculate that when the atom's in a certain quantum state? Yeah?
Use the way that we did, just like use dipole.
Yeah, I need to find the matrix element, or another way of saying it, I need to find the expected value, right? So, I mean, the dipole, as in anything in quantum mechanics, there is an operator that describes the observable, right? So there's an electric dipole operator, and I want to know what is the expected dipole moment, right? I mean, it's not, unless it's in an eigenstate of that, it's not going to be a definite thing, but I can ask what's the expected value of that, right? That's quantum mechanics. So I have the electric dipole operator, which in our two-level approximation only has the off-diagonal elements, and we took the matrix element here to be real when we thought about this as a pi polarization on our two-level atom, right? So that's my dipole operator. Everyone clear on this? Where this thing is the expected value counting the matrix element, off-diagonal matrix element, which is the same thing as this because it's taken from 0. Which we can do from our choice of the phase of the wave functions. Okay, so this is in the Schrodinger picture. What I'm interested in is what is the expected value of this, say, along the direction of the laser. So I'm going to take the laser here to have some electric field, which will be the real part of some polarization, which is linear polarization, and then some. So that's my laser electric field. Okay. And I want to find what is the dipole moment induced along the direction of that. Okay. Now, so how am I going to do that? That's right. So I need to look at this in terms of, I need to find the state of the system, which is the density matrix. And I take the trace of rho with that. Now, when we've done this, we haven't always done it in the rotating frame. Okay? So we have to do this all in the same picture. If we've written the state in the rotating frame, then we have to write the operator in the rotating frame. Otherwise, we're not doing it correctly. Okay. So this is going to be equal to, as Dave said correctly, the trace of this with rho, which is dEg dot into epsilon, and then I take the trace of rho with this, and how do I do that? The trace of rho with that? Now again, I got to be careful about this because this is all going to be done in the rotating frame. Okay, so let's go to the rotating frame for the operator. Our state is already written in the rotating frame. We've already done that. So, go to the rotating frame. Our U, we rotate around the z-axis by the angle omega t, where omega is the driving frequency. In this case, the laser frequency, right? So the dipole operator in the rotating frame, I have to do this unitary transformation on it, and that becomes d dg e to the plus I omega rt plus dp e to the minus I omega rt. So, in the rotating frame, this thing then becomes the following. Where this is now in the rotating frame. Okay. All right. So, if I want to know what this is as a function of time, I have to solve my differential equations. And generally, it's going to oscillate in some way, all of these things. But what I'm interested in at the moment is after the transients have died off. Okay? So this thing will come to some steady state. That is to say, this amplitude in this coefficient in the rotating frame comes to some steady state after because of damping. Okay? So the in steady state, that is to say, after the transients have died off, the matrix elements stop evolving with time, which means that the derivative of this guy is 0. So that tells me that the steady state value of the octagonal matrix element is related to the steady state population inversion through this detailed balance. Okay. Or, putting that together, we've got, got the signs right. Solving that equation. Okay? Now, let's consider the case of weak driving. Let's come to this board. So this was for pretty strong driving. I got a good amount of population up towards the excited state in this case. But if the system starts in the ground state and I don't drive it very hard, and we'll have to quantitatively figure out what that actually means. What does it mean to not drive that hard? Then we don't expect very much population to get out of the excited state. So for weak driving, again, we will have to make this more quantitative, what this considers. Then what we would say that in steady state, to lowest approximation, the particle stays pretty much in the ground state. The atom is pretty much in the ground state, in steady state. And not much ever gets into the excited state. Again, we're going to have to figure out under what that approximation means exactly, but for the moment I'm being loose about it. Okay, yeah?
It's interesting, in this case, a mixed state could evolve into a nearly pure state.
Well, that is true. I mean, it is, and that is the case. We know that, suppose I just put draw a little picture over here, pop right here, you know, already said some room. Let's just say we had the following thing. Let's say I somehow had a state that was some mixed state, right? Let's say it was a completely mixed state. It was a 50-50 mixture of excited and ground, and then it just turned the laser off. What will happen? It will decay to a pure state. And if I start anywhere and I turn the laser off, it's going to decay to the ground state. That's an example of cooling. So dissipation can remove entropy and make something more pure if you set it up right. So just because I have a coupling to the environment doesn't necessarily mean I make it more mixed. I could also make it more pure. That's another story. All right, so this is the case I'm going to be looking at here for weak driving. We'll come back to that, what that means, how I can, under what conditions of the laser is this going to be a good approximation. In that case, then what we have then is that the off-diagonal matrix element, rho EG in steady state, is approximately equal to, here's one of my minus signs, minus I omega over 2 I delta minus gamma over 2, right? From that equation. Which is equal to, is equal to multiply top and bottom by I omega over 2 minus delta minus gamma over 2 times, oh God, don't do it, don't do it, too many minus signs, not enough time. All right. Oh God, somewhere I already made a mistake somewhere already. How could that possibly be? That's right, that's right. So then I multiplied minus I. Multiplying it minus. Oh no. Right, sorry. If I multiply top and bottom by I, then this becomes minus. Okay, good. Phew. Man, oh man, oh man. Oh well. I don't know where I went wrong. But I think there's an overall minus sign, and I swear to God I checked it. I checked it because this should be this, but this should be a plus and this should be a minus, and I'll double check, because I'm pretty sure this is, what I'm supposed to get is this. Multiply this top and bottom by minus I. So I put a big question mark here, and I'll come back to it. I really thought I had it right. But I'm pretty sure this is right. We'll find out in a moment. Because if I look at this, and here's the other thing, so here, you remember that omega was minus d dot E dotted into the electric field over H bar. So, with that said, where's our electric dipole over here? So my electric dipole over here, multiplying this in, this tells me that is equal to 2DEG, so that becomes DEG dot epsilon squared. I have over delta plus I gamma over 2. I got a minus sign. Sorry. Let me write this again. Sorry. The dipole moment adding to epsilon as a function of time is equal to the real part of minus dEg epsilon squared over HR delta plus I gamma over 2. I hate these signs. All right. So, what does that look like? Yes?
How'd you get that implication arrow in which you?
I just took this and I plugged it in here. So this is the dipole matrix element in steady state, and I plugged it into that expression. All right? Very good. So, what do we see about this then? Well, what we see is that we have an induced electric dipole moment. And that induced electric dipole moment is proportional to the applied field. Right? So what is this coefficient? It's the polarizability. That's the atomic polarizability. Right? So, what does that look like? It has a real and imaginary part to it. As a function of the detuning. Sorry, I'm listening. It's a Lorentzian, right? This is the complex Lorentzian that we studied in the context of a charge on a spring. It has the imaginary part of this, so this thing is equal to dEg squared it has our famous Lorentzian line shape with the dispersive real part and a Lorentzian imaginary part with a full width half maximum, which is given by gamma. So, an important lesson we learn here is that a driven two-level atom, when it is weakly driven, looks like a charge on a spring. And you should think about it just like a charge on a spring, where you are driving the electric charge away from equilibrium, and in steady state, it oscillates not at the frequency difference between the excited and ground state, but it oscillates, that charge distribution oscillates at the frequency of the laser, which could be off resonance. And it has an amplitude, a certain amount of amount that is in phase with the laser, and a certain amount that's in quadrature, or 90 degrees out of phase with that laser, which depends on the tuning. So how, in what way is this different from the Lorentz oscillator? Well, what did we find for the Lorentz oscillator? Well, what we found was also this was equal to the real part of some alpha. But alpha was right? And the difference was just this ratio. This was really what we call the oscillator strength, the fudge factor. So there's really, the only thing that is different is the strength of the polarizability, but we can fudge that with the oscillator strength, as we say. So, in this problem, if I think about the motion on the blocks here, in the absence of damping, let's say I was detuned in some way, what would this block vector do? Let's say I was detuned to the red, right? So I have some amount on resonance and some amount of detuning. This is my omega total. This is the torque vector. What will happen to the block vector? It'll precess, right, by some amount with that Rabi frequency. Now, of course, this whole thing is a whipping around the z-axis at the laser frequency, because we've gone into the rotating frame. Okay. So it's whipping around at that frequency, but in this frame, it's doing this. Okay. Now, in the presence of damping, what's going to happen? Well, it's going to, ultimately decay to some point and come to some steady state in the rotating frame, close to the bottom of close to the South Pole, to the degree to which that was a good approximation, which we'll have to see. in the lab frame, this thing is rotating around at that frequency. So the block vector is just oscillating in the lab frame at that frequency with a certain amount of coherence in the problem. It has some amount of coherence, and that amount of coherence is this. That's what the off-diagonal matrix element was. So, you know, if I thought about this as a pure state, which it isn't, it would have some amount of, well, let me write it as what it actually is. It has some amount in the excited state, some amount in the ground state. And these guys in the rotating frame, we have, now going back to the lab frame, we have something like this. That is to say, we get some oscillation in the superposition between ground and excited. And that's just an oscillating dipole. Why is that an oscillating dipole? Yeah?
The ground and excited have different dipole moments.
They do, right. And I mean, I want to use your point is, let's look at the wave functions, right? If I thought about this, let's say the ground state, here's the nucleus, here's the ground state. It's an S state. I got the first excited state. Let's say it's this P state, which has this plus, and it had the phase of the wave function is positive here and negative here. I add these together in superposition, and I get the cloud is sitting up here of electron, and the nucleus is sitting up here. That has an electric dipole moment, right? The dipole moment goes from positive to negative charge. But then, at some later time, it's a minus sign, and this thing is on the other side. So I have an oscillating charge distribution. I mean, it's still physics. It's not just a bunch of abstract wave functions. There's an electric distribution that is separated here. Okay. Now, the degree to which this electron is pulled away depends on the strength of the driving and how close it is to resonance, and that's given by this expression. Okay. So we should just think about this like a charge bound to a string. All right, very good. Yes, sir.
I'm kind of confused. Why in the lab frame is the rate it's oscillating driven by the laser frequency and not just the natural energy separation between the two levels?
Because that's how we went to that rotating frame.
Wait, so I thought this was in the lab frame, this row dot, or this row. I guess I'm confused. Which frame are we in for this equation?
This one's in the lab frame.
Okay.
In the rotating frame, this was constant,
Yeah,
right?
yeah.
But our rotating frame transformation with respect to the driving frequency.
Okay.
Because it was in that frame that we can make the Hamiltonian time independent and solve those equations. So we went to a frame such that these guys, we could solve for these equations.
But are these row EGs time dependent?
Not in steady state.
Not in steady state.
Okay. In the transients, absolutely.
Okay.
That's when something's happening, right? But once we get to steady state, the coherences and populations are in steady state. But that doesn't mean that the dipole moment the expected value of the dipole moment is not changing in time. This is what we found. And it oscillates at the driving frequency. Now, the way we did that was a bunch of mathematical transformations. We could have done any transformation we liked that made it easy to solve. But this expectation value is independent of the picture, whether we're in the lab frame or the rotating frame, the interaction picture, the sort of, it doesn't matter. This can't depend on that, and it oscillates at the driving frequency. And it's equivalent to the following problem. Here's my slinky. You ready? Everyone knows what a slinky is? This is its resonance frequency. You see it? Now, I'm going to shake this slinky. At what frequency is that slinky going to oscillate in steady state? My frequency is going to go like this. It's not going to go like that. So when you drive an oscillator in steady state, it oscillates not at the natural resonance frequency, it oscillates at the frequency that you drive it at. So does the atom. Okay? I love my slinky kid. I heard hearing, does anyone know what a mime is? Okay, because there's a joke on Wait, Don't Tell Me last night about, you know, how millennials don't know what mimes are. Like, what are you talking about? I don't know what a mime is, but anyway, so that's my... Someone had a question. Yes?
Don't we expect the steady state to be mixed?
We do.
Okay.
We do. And I don't, I'm sorry, it's not on the surface of the sphere here. It's inside at some level. You're right. Very good.
Is this, you have the thing in the box, expectation d dot epsilon. Is that thing complex?
No.
So does the real go further in the box?
It's the real part of this whole thing. Sorry. So this is the real part of this. This is a complex polarizability, which has a real part and an imaginary part. The real part of this tells me how much of the dipole moment oscillates in phase, and the imaginary part tells me how much oscillates in quadrature, just like we saw for the Lorentz oscillator. Yeah?
So since we're weakly driving, we're
Yeah.
using S, right? And then we add in a little E.
That's correct.
Is this like a dress state picture?
That's an interesting question. The answer is no. We'll come back to that. Dress states are eigenstates, so they of the total Hamiltonian, and so they do not evolve in time. We'll come back to that soon. What we're doing is we're turning on the laser quickly. It's like what in elementary quantum mechanics you might have called the sudden approximation, where you change the Hamiltonian very quickly. All of a sudden the system says, oh my God, I'm not an eigenstate anymore. And it has to evolve. It's now in a superposition and it will oscillate. All right, good. So, Manuel, you had a question?
Yeah, so for the answer of Matt's question,
For what question?
So in that case, do you need to include in your Hamiltonian the Hamiltonian of the light itself, or you can still consider it semi-classical in some sense?
We are not quantizing the field yet.
Okay.
So all of this discussion is related to treating the laser as a classical field. Okay. There is, of course, the vacuum, which is kind of in the background, which is the physical origin of the spontaneous emission, but we're not including those dynamics explicitly we've created a phenomenological theory which then gives us damping, in the same way that we put friction into Hooke's law without dealing with the microscopics of where the friction comes from. We just have a friction coefficient. We will, over time, see modifications of this and what does it mean to treat the field classically. But first we gotta quantize the field, and we haven't gotten there yet. All right, so pissed that I got this signed on because then I don't know if anything the rest of it, but let's see. All right, so now when we come steady state is really detailed balance. Meaning that energy is going in and energy is going out. And in such a way that they balance one another. So that there's no change at some point. It doesn't mean nothing's happening. It just means that there is detailed balance. So when we think about this kind of detailed balance, we can think about rate equations. So rate equations are the equations, it's equivalent to the full master equation after coherences have reached steady state. So after a few lifetimes, a few nanoseconds of interaction time of the laser with my atom, this coherences have come to steady state, those coherences that we say. Now we can ask, when that's true, what were the population equations, right? So we have this equation, we said that this was the master equation, which was the full equation, said that the population in the excited state would decay, and it would be driven by Rabi oscillations. Which is equal to minus gamma rho Eg minus omega times the imaginary part of rho Eg. This minus its complex conjugate over 2I. Yeah, okay. Oh, sorry, this is a rho E. So this is an exact equation. This is the master equation. Now what we're going to do is say, okay, these coherences have come to steady state. Okay? So in steady state, so now I can write the rate equations, says that in steady state, the coherences are related to the population inversion. So plugging in that equation that we got, making this now steady state, gives us the rate equation. And with not trying to do the algebra on the board, this is the answer. So this came from plugging in what this is related to the population inversion as the coherences came to steady state. So I'm going to write these equations now, defining population in the excited state and population in the ground state. So let Ng be defined to be the population in the ground state, and N sub E equal the population between the excited state. And what one finds then is that if I look at that equation, and E dot is equal to minus gamma plus something I'm going to call gamma spin and E plus gamma stem and G. Where gamma stem is defined to be equal to omega squared over 4 delta squared plus gamma squared over 4 times gamma. Okay. Of course, this is equal to the population in the excited state changes opposite to the ground state. And I get that. What are these equations? Well, these are like equations of population of rabbits and foxes undergoing some kind of dynamical change where the population changes due to certain rates. So this is the kind of picture you see in an elementary quantum mechanics or laser physics type book where I say, okay, I have some population in the excited state, some population in the ground state. I can have population going from ground to excited at some rate, which we're calling gamma state, and can go from the excited state to the ground state through, in this case, 2 rates. One is it can spontaneously emit with rate gamma, or it can stimulatedly emit and these equations came from the master equation after the coherences had come to steady state. Okay, yeah?
On the one hand, you have the formula relating rho Eg to the diagonal it goes, but on the other hand, I remember vaguely that they said rho Eg decays, the off diagonals decay exponentially in time.
Everything is decaying exponentially in time. The populations are decaying exponentially in time, and the off-diagonal elements are decaying exponentially in time. But they're also being driven. They're being driven by the laser, which is inducing some coherence, and they come to some steady state. And what we just spent the last half hour doing, showing what the coherence, to what steady state did the coherence come to. Now in that case, I set this guy equal to 0 and this guy equal to 1. I looked at the case of weak driving, but now I'm looking at a more general case. And in steady state, the coherence I get is not decay to 0. It decays to something that is proportional to the population version. And the population version that I have in steady state depends on how strong the laser is and the tuning, as we will see. Yeah?
What exactly does it mean to be steady state if we had a physical system? Because, like, I guess if we're looking at all our atoms, sometimes we'll accidentally measure one, right? And then
So this is the situation where we're looking at this spherical cow. It's an idealization where we just have an atom, it's assumed to be fixed somewhere, and we're shining a laser on it. And what will happen is there will be a transient. Eventually, there will be a certain, the density operator that is our distributed system comes to a steady state, no longer changes in time in the rotating frame. And at that time, the probability to be in the excited state and the probability to be in the ground state no longer changes with time. And the coherence in the rotating frame no longer changes with time. That's what we mean by steady state. Now, of course, the reason it's in steady state is because there's a detailed balance. So in this rate equation picture, we think about we don't think about the wave function. I mean, this is the way that early to mid 20th century physicists thought about physics, is that there are energy levels and rates and cross sections. And you never ever think about the probability amplitude in your life. And you just think, oh, what my laser's doing is it's making population go from here to here, and I forget about this. What happened to the Sherman equation? I don't know. I just have some populations. But we see that follows from first principles from the master equation when we have taken this to steady state. Now, what's going on in this case is that we have, if we thought about the population or the probability to be in the excited or the ground state, there is absorption and emission. There are two processes that we think about in this. In emission, there is spontaneous emission and stimulated emission. And in the case of absorption, well, it's only stimulated by the light. Okay. And that emission and the stimulated rate is here. Now, again, if you're a 20th century physicist, or you never learned anything about the Schrödinger equation, you have to know something about the Schrödinger equation. But when you think about the rates, you just whip out the only thing you got, which is Fermi's golden rule. Which tells us something about the rates of transition in perturbation theory. Okay? So in perturbation theory, we would say that there is a rate, a stimulated rate, a rate of absorption, which is 2 pi over h bar, the matrix element of the interaction Hamiltonian, the positive frequency component, to go from the ground state to the excited state, and then a density of states at the excited state equals, this is Fermi's golden rule. It says, I look at the interaction matrix element, the square of that tells me something, and then I have the density of states factor. So let's see if that actually gives me this. The answer is yes, but what do I got? I got the ground state. I got the excited state. Oh my God, the rate is that time. This has some line width to it. My interaction Hamiltonian here is our laser Hamiltonian, which is equal to h bar delta over 2 sigma plus sigma minus. This is related to the positive frequency component. This is the negative frequency component. And I have this Lorentzian line having to do with the fact that I have this. So, I just want to quickly now solve for this in steady state. Let me define this as we do as some factor, which I will call S over 2 times gamma, where S is defined as omega squared over 2 delta squared over what's gamma squared over 4. It's known as the saturation parameter, for reasons that will become clear in 2 seconds. So, let's solve for what is the actual population in steady state. The ground state is 1 minus the excited state. So I can write this like this. Having used this is 1 minus this. And in steady state, this is 0. There's no longer any change, which says that in steady state, that's how much population is in the excited state, which is equal to S over 2 over 1 plus S. So, to answer the question, when is the population in the excited state, in steady state, going to be essentially 0? And the excited state population, the ground state population, essentially 1. So, weak driving implies weak saturation. Which means S much, much less than 1. And this is S. So, if I have a certain amount of laser intensity, and I want to know whether when I shine this laser on my atom, whether in steady state there's going to be a non-negligible amount in the excited state, in steady state, I got to calculate this. I got to know how far I'm from resonance and what my intensity is. Because the Rabi frequency is proportional to the electric field. The Rabi frequency squared is proportional to the intensity. So on resonance, when delta is 0, this is the saturation parameter. So, roughly speaking, when the Rabi frequency is on the order of the line width, or the spontaneous emission rate, I start saturating. If my Rabi frequency is very, very small compared to the spontaneous emission rate, I never really get very far out of the excited state on resonance. Off resonance, now this thing is proportional to the intensity. Right? Because the Rabi frequency is proportional to the electric field. The Rabi frequency squared is proportional to the intensity. This is a dimensionless number. So we often write this as the intensity over the saturation intensity. The saturation intensity is a property of the atom. It depends on the dipole matrix element and all that stuff. It's a characteristic intensity of the dipole transition. So, for an optically allowed transition, like in an alkali atom, the saturation intensity, I know, because I used to work with this stuff, is about 1 milliwatt per centimeter squared. So if you shine a laser beam which has 1 milliwatt of intensity shined into a spot on every centimeter squared, then you run on resonance, you're going to start saturating the atom. Okay?
This is for gases, right?
Yeah, this is for just, a typical hydrogen-like. It's just to give some of the experimentalists in the room a notion of what are we talking about. Yeah. But anyway, the point here that I want to close with is this comes back to what we said at the beginning. When I shine a laser on an atom and the saturation parameter is small, I can think about that as a Lorentz oscillator. Basically, it's a charge on a spring. It's when it's undergoing Rabi oscillations and I'm getting major population out that it's really, that's when it starts thinking something that's quite different from Lorentz oscillator. So the final point I want to make here, and the rest you'll just have to read in the notes, is what happens when S is big compared to 1? So as S goes to infinity, not this limit, but the other limit, as S goes to infinity, what happens to the possible steady state? What's the best I can be here? Half. So as the laser physicists know in the room, you can never invert the population in the two-level system by just driving it. You need a third level. So in steady state, if I'm really driving the system hard, I say I saturate it. That's why it's called the saturation parameter. And now I ask you the final thing. What is the state of the system in this limit? Not when I'm far, when this is true. It's right, this is the completely mixed state. When I drive the system so hard, it kind of equilibrates to a completely mixed state with no coherences and equal population inside the incremental state. It's only for weak driving that I have induced coherences.
How can we understand endurance?
The fact that it goes to a mixed state?
That the S less than 1 gives more coherence, and the S goes to infinity, it gives less.
The reason physically it works is that when the issue has to do with how important spontaneous emission is. So for weak driving, I'm just not getting very much into the excited state. And therefore, there's very little spontaneous emission. Therefore, I maintain a lot of coherence, comparatively. It's never a lot of coherence. The amount of coherence I have is always proportional to S. So S is small, right? The only way I can get a lot of coherence in the system is not in steady state. I have to do a pi/2 rotation very quickly, right? Compared to the spontaneous emission rate. And then I have a lot, so I have to be in that transient regime. Something extremely non-classical, something that's not at all like a charge on a spring, in order to make the system in an equal superposition of ground and excited state. Of course, it wouldn't last very long, because that coherence would decay in a couple of nanoseconds. If for a typical optical transition, I need to have a much longer lifetime system in order to create that kind of coherence that would last a long time. All right, I kept you all very long over time. I'll take some more questions. Have a great fall break. Use this opportunity. Shop.